Hello. Morning, everyone. Exactly. Okay. We'll get started. Hello, my name is David Talby, and this is my friend Alex Thomas. And we are going to talk to you today about an open source library built on top of Apache Spark ML, enabled really for you to get best-in-class both performance and accuracy on natural language processing and natural language understanding tasks. So hopefully when you leave here, you at least get a taste of it and you know where to go and, and start using it. So we're going to talk a little bit about what we mean by natural language understanding, because some of the algorithms here you need, some of them you may have tasks where you can just do without. So we'll see when this is actually needed. We'll introduce the library, the main design principles, and what's really new about it. And then Alex will walk through one just code example in Python, so you could see really how simple this actually is to use in practice. So natural language understanding is a hard problem. In fact, it's one of those problems that are termed as an AI complete problem, in the sense that if you solve it, you would solve strong AI, because of the just large amount of this nuance and emotion that go into human speech. So we're not going to solve all of it, but what AI can do today really well is solve very, very specific problems, as well or even better than people, so that we can do. And let's see how we got there technically. So when we started looking at electronic documents, we basically put them in a search index, and you could do queries. So you could look for keywords, and you could do search. And we spent a whole lot of time optimizing those search and indexing and lookup pipelines. So we looked at different tokenizers, and we looked at how we can work with different languages, how we can look with HTML and PDF and Word documents, how we can change ranking so that we know that if something appears in a header, it's more important than the word in the middle of the text. And we did that for about 10 years. And you can do, that was so much better than reading the documents one by one. So this became very popular. And this is just a basic search that's been commoditized at least a decade ago. When we went slightly beyond that, and this started with the main search engines and propagated from there, we did semantic search. And these are 5 queries that if you try them on Google ES, you would get the results you'd expect. And basically what this means, look, we are no longer doing keyword matching on the text. What we are trying is to understand the intent of the query. So if I type in NBA, I want the latest scores, so I want tonight's game or the last game, and obviously based on where I am geographically, based on time in the year, this is going to be different. If I'm doing a restaurant search, so obviously I want things that are near me, I want things that are open right now, right? And similarly, if I look for a cheap dress does not cost as much as a cheap pen, or as a cheap car, or as a cheap house, right? So really, first of all, you need to understand the domain. You need to understand that within the domain of clothing and shoes, what's really important is gender, size, the occasion, the cost. Then you need to try to find those things within the text, and that's what you mesh within search. All of that is still not what we normally consider natural language processing or understanding. For natural language understanding algorithms to apply, we are talking about problems where we really need to begin to understand the grammar of a language. So here's a healthcare example. And if you're trying to run any queries on a set of patient records, one of the things that are really important are whether the patient has the disease or does not have the disease, or maybe had the disease, or had the disease when she was 9 years old. Those are clinically completely different things. And if I'm trying to do things like people to a clinical trial, or trying to predict who is at risk for a certain kind of disease or complication, those are the key things I need to know. And then anything you do that is based on keywords or synonyms or word embeddings for relationships is not going to help, because now you're at the point where you need to understand in the English language grammatically, how do we say negation, right? How to say that something is happening versus not happening. And that's going to be different in French or in Russian or in other languages. We need to understand how we say that something might happen. We need to understand what is the order of things, right? So am I taking this medication because I had the symptom, or do I have the symptoms because I'm taking the medication? What happened before what? Okay, and now I'm getting to a point where I really need to understand the grammar. I need to understand how the language is built. Okay, and there's a whole set of algorithms that come into play. So I need to understand parts of speech. I need to understand if the word clean is a verb, is a noun, is an adjective. I need to do correct resolution. So when say Jane is at risk for flu if she is not vaccinated, I need to know that the word she refers to Jane, right? Not to the vaccine, not to something else. And this obviously depends on context. I need to do entity recognition, so I need to understand that influenza and flu are basically the same thing. I need to understand that RIDT, which is a noun here, is the test for influenza. So if the test is clean, meaning it's good, it means that your diagnosis for influenza is negative, right? And I need a domain understanding in addition to the grammar. And those are the kind of algorithms that we're talking about. So there are a few things that make language very hard. So language is very nuanced. So here are some examples for ways to me to say that I agree with you. If you, you can Google, 500 ways to say I love you, 500 ways to say I agree. There are more than 500. And if you look at those examples, you see that they, yes, all of them may mean that I agree with you, but they say very different things. Right? They are not the same. Because when we speak, we say a lot about, it's not about what I say, but how I feel about it, how I feel about you, how I feel about the situation, right? There's a lot of nuance that goes into speech, which you really have to understand, right? Because sometimes it's not about the fact itself. Human language is very, very fuzzy from a computer perspective. So to say that something is blue is a very fuzzy concept. To say that, I did something, it's a very fuzzy concept. To say that, someone is young or old or a child or unwell, those are all very fuzzy concepts, and they mean different things in different contexts, which means that you need to build domain-specific natural language models to really understand them. And that's very inherent in just how we speak. Language is highly, highly contextual. So this is a great example. So when a doctor writes something like, patient denies alcohol abuse in a medical note, there's really only one meaning to it. The meaning is, I suspect this patient is an alcoholic. Okay? And the reason to write it this way is because patients can have access to their medical records. So as your doctor, I cannot just write, no, this is a textbook alcoholic if I've ever seen one, right? Because then you're going to see it and you're going to get mad. Okay? On the other hand, I don't want to write nothing, because this goes on to other clinicians, and I don't want you to get medications that may conflict with alcohol and hurt you badly. Okay? So this is the code word. Okay? And the only way you would know that this is the code word is if you understand not only the specific area of medicine or family medicine and substance abuse, you also need to understand the context of who is writing this, who is going to read this, and why people say things the way they do. Okay? And this doesn't only happen in healthcare. This happens when you write SMS messages, when you write emails at work, when you post on social media, when you call customer service, right? When you write an academic paper, right? You write in a certain way, use certain words to mean certain things, right? That are often implied or not written. Language is very medium specific, and it's really simple. Like we use a different vocabulary and different grammar. There are some assumptions. So if I say see you in 15, it's usually 15 minutes, okay? But obviously it depends on some other context we do not have here. And language is domain specific. So this is an example from a Netflix SEC filing. It does not actually say anything. It's legal boilerplate, right? And you have domains like finance and legal where you have tons of this boilerplate text where you hide things in plain sight in a large amount of text. So overall, if you look at the combination of all of these, understanding language, understand why someone says something, what they actually mean, is very, very different from reading a string of text from an algorithmic perspective. There is much more context that you need in order to do it, and that's where the difficulty is. The good thing is that it's very doable, also for hyper-specific tasks, right? The way we do all of our machine learning and AI today. And really, we can get human or better than human performance for all of these tasks. And really, we can move away from, does this social media post contain an offensive keyword to is it offensive? Okay, and obviously, you can be very offensive without using offensive words or vice versa. Right? So for example, when there are two situations to use offensive words, either when you want to hurt someone or, you want to use profanity, or when you're very close with someone. Okay, so when you're very friendly with someone, you also tend to use those terms. Those are very different contexts, and you need to be able to differentiate. Similarly, if you're in a customer service situation, the question is, okay, what is this customer asking about? What product, what is the problem? Okay, so if the customer is complaining, if they came in, they had a really bad experience, was it the waiter, was it the food, was it the parking, was it the bill? right? Now those are things we can do, and the way you do them, you need a set of NLP algorithms, so you need tokenizers, you need lemmatizers, part of speech tagging, dependency parsing, name entity recognition, and you need to combine them with machine learning pipelines on top of them that give you your prediction, your recommendation, your classification results. Okay, and those are the things that we were looking for a way to build. What we'd like to do now is introduce the Spark NLP library, and that's a library that we released as open source back in September. Since then, we've had, I think, 15 or 16 new releases, constantly about 2 or 3 weeks, and it's been picked up by dozens of projects that we know of that are using the library, and open ticket, contribute, ask us questions on our Slack channel, and build production projects. When we started, there are tons of NLP libraries that are out there. There's Stanford NLP, and there's OpenNLP, and there's Spacey, and there's NLTK, and there's GenSteam, and there are libraries. The cloud providers have their own libraries. When we started, really we saw a big gap in not just the Spark ecosystem, but really more generally in the Java and Scala ecosystem, in terms of having a library that is actually best in class in terms of performance, in terms of accuracy. Many of the libraries that are out there today have had academic beginnings, which means really they are more optimized for experimentation, right? Being able to use all the algorithms approaches, instead of really being optimized for industrial-grade, production-grade usage. Spacey was the first library that really had that focus to begin with, but that was focused really for the single machine, small data use case. And as we show, even for those use cases, we can actually leverage Spark and get far better performance out of it. And there was really no library that was good, not even excellent, just good, for your own custom models, which is really what you need to do when you have a domain-specific problem, like any of the problems, any of the use cases we spoke about. We need to understand a context. So the design goals for Spark NLP were, first of all, just really state-of-the-art performance and scale. We want to do something that was far better than anything out there. We want to have something that enables you to very easily reuse, specifically starting with the Spark ML code base, but then the entire ecosystem around it. Right? There are a lot of libraries that integrate very well with Spark. So we did not want to rewrite our own TF-IDF and LDA when all of these were available as open source, distributed, widely used, widely tested libraries. We want to make it very easy to reuse. And from the beginning, we started this for not just production use case for large enterprises. There are several large enterprises customers we started projects with. So the goal was we have something that's production grade. The library is definitely generally available. It's a Apache 2.0 license, so it's open source, commercially usable. There's an active full development team that's continuously building new releases. And there's active documentation and support channels for it. So you're most welcome to start using it. In terms of how the library is built, so the library is a native extension of Spark ML. We wrote it natively in Scala. We can work on data frames directly. So a lot of the performance benefits that we get are from just basically zero memory copying and using and taking advantage of some of the core Spark optimizations, both on a single machine and on a cluster. So on top of the core Spark, where we have RDDs, we have data frames, then we have the Spark ML APIs. And for this library, like an NLP pipeline is the Spark ML pipeline. There's no other class, there's nothing else. We just reuse the exact same. On the right, you can see we can reuse everything that's Spark ML and Spark MLlib, and there are quite a few things that are already there. Stopword removal, TF-IDF, bag of words, like the basic stuff is there. And then what we've had to add on the left side are really the core NLP algorithms, starting with tokenizer, normalizer, stemmer, lemmatizer, so the core things, and then adding more interesting algorithms like automated spell checking, name entity recognition, entity resolution, sentiment analysis, sentence boundary detection, and other annotators that are really specific to analyzing human text. In terms of how this looks in practice, and really just to show how easy it is to use and integrate with the Spark ML ecosystem, here's basically how a pipeline looks like. So the pipeline object is a Spark.ml pipeline, right? There's no other class. And within it, you can build one pipeline that in this case starts with just 4 Spark NLP annotators, right? So those are algorithms that the library includes. And that's how here really you begin your feature engineering pipeline. Then we use stopover removal, TF, and IDF, which already come with MLlib. But as you see, like you can't even tell where one begins and the other ends. And then we run LDA, so we run a machine learning pipeline. And that's also really important because really the main thing you do with NLP algorithm results is you use them as features for machine learning problem, right? So nobody needs to name entity recognition just to have the entities. You need them to do something with it. Most commonly, you need a machine learning pipeline. And one of the things this enables you to do is really avoid what you have to, what you had to do until today really with every other NLP library, which is to split off the NLP sections from the rest of your feature engineering and ML pipeline. Now you can do it as one pipeline. All these pipelines, they're serializable, okay? So you can reproduce them. You can scale them, right? So they were, either locally or distributed. And they're tested with the entire Spark 2.0 code line. The other cool thing here is that once you've defined the pipeline, then you call fit to train, okay, or you call transform to actually do inference. At this point, you ask Spark, okay, you tell Spark, okay, here's my entire pipeline, defined all of it, now go run it. So all of the optimizations that are built in terms of the query planner, the execution planning, caching, just-in-time compilation, everything that Spark does for us, we can reuse, okay? And we give Spark as the input really everything we actually want to do, okay? Starting with really basic tokenization, normalization, to the ML parts of our pipeline, right? Where the question is, okay, which features do you cache so that we can actually use them, right? When we get to do, whether, LDA, or whether, we build a neural network, right? Or whether we do grid search or hyperparameter optimization at the end. And that gives us a huge performance boost. And one of the cool things to know is that this is, when we started, we said, look, of course on a cluster, this is going to do like 3 orders of magnitude better than anything else, right? Because really it's the only distributed NLP library that's open source. But really the first benchmark we tested was on a single machine, okay? And in this case, you're seeing a benchmark on a dev laptop. That's an Intel i5, 16 gigabyte memory, 4 cores, so very kind of mid-range dev machine. Because really most people start, just start prototyping locally. And this is a simple pipeline. We did sentence boundary detection, tokenization, and part of speech, okay, and train the custom model using also not a lot of data. I mean, you can see, we used either 100 kilobytes of data or 2.6 megabytes of data. So, homework exercise style of examples. And as you saw, on the 100 kilobytes of data, the library was 38 times faster than Spacey. To train a model. On 2.6 megabytes of data, it was 80 times faster. We did, and it gets worse, so at some point, really, we just stopped running it. Okay, and this is the single machine use case. Okay, and this says a lot, by the way, about how well Spark has been optimized for single machine. Okay, that's one thing. And really, for me, this was a surprise, because look, if you look at something like Spacey, Spacey is optimized C code with a very thin Python API. So when we started, we said, look, we have the JVM overhead. We have the Spark overhead, right? The assumption was, look, 100 kilobytes we're probably going to be slower, and at some point it catches up. But that's the reality of it. The reality of it was, even if you're looking at basic prototyping, you're going to get here something that would give you really between 1 and 2 orders of magnitude of improvement, which, as you know, makes a huge difference really how fast you can experiment, right? If this is part of your feature engineering and ML pipeline on top of it. When you scale, as you expect, this scales as well as Spark does. So this was a really simple benchmark when we said, let's take exact same code, no configuration, no code changes whatsoever, just run it as, as an EMR job on a 4 machine cluster, and we got 2.5x speed up. But obviously, when we run this on a 40 machine cluster, or when you take some time to optimize the Spark properties, you can get really near linear speed ups on those algorithms. So really, if you're looking to do something where you prototype, but then you have the ability to scale, then really you have something here that other libraries cannot provide. Those benchmarks are available as an O'Reilly blog post. It's actually 3 blog posts. You have 15 pages of all the gory details if you really want to go and reproduce the entire benchmark. It's Spark 1.5. It actually already came out 2 months ago. We're at 1.5.4 now. 2 things happened. The main thing was we went out with light pipelines. Light pipelines give you basically another order of magnitude of performance improvements if you're really working on small data, so up to 50,000 documents that you're analyzing, because basically we cut really some of the Spark over there and did a lot of memory optimization. Other than that, really, if you're looking at large data sets, this is really your only open source choice. And since really, today, it's either Python or Scala, it's on Spark, very easy to use. Not only if you consistently work on a large data set, even if you have one-off thing and you want to, to launch an on-demand cloud job, right? Really to be able to experiment faster. So that's the overall. That's the design. Quite a few projects using it now. What I'd like to do now is hand off to Alex to show a code example in Python of really one sort of classic, simple use case of how this works in practice. Thank you.
Okay, so let's look at some actual code. I mean, David already showed that snippet of the building the pipeline, but let's look at a little bit more code here. So there's a home page for the Spark on NLP, and it's right there. We got the GitHub, all that nice stuff, and they have plenty of really good examples there. So I encourage you, if you're interested, go there and look at those examples. But let's look at something in more detail. So here, we're just going to import some stuff. So we're going to bring in the Spark ML pipelines, right? Because we want to build pipelines. We're going to bring in our annotators. So these are all the annotators that are exposed through Spark NLP. And then there's some Spark NLP-based stuff there, a document assembler and a finisher. I'll explain what those are. So the document assembler. So one way which you can split up NLP libraries is there's functionality-based libraries and there's annotation-based libraries. Functionality-based libraries are something like NLTK or Stanford NLP, and really what there is that they're a collection of algorithms and models that are built for solving different problems, and there's no concept of a document. There's just sort of like, oh, you take in these strings or arrays of strings and you output them. An annotation-based library, something like Gate or Spark NLP or Spacey, you have this idea of a document that contains text, and that as it goes through your different processes, it adds the annotations, which is the things you found, tokens, sentiment, what have you, into the document. So the document assembler takes your text and builds a document for you. So you can send it through the pipeline and add all your other stuff to it. So the first thing we're going to add here is we're going to add the sentence detector. So what the sentence detector is doing is that it's segmenting your document into sentences. So the reason why, of course, that's useful is that imagine if you're looking at windows of words, you don't want those windows to span over sentences because that would just be nonsense. So you want to break it into sentences first. Then we have the tokenizer. Now, theoretically, you could actually have a tokenizer first and then a sentence detector, but it seems like it's generally implemented this way, where you have some sort of sentence detection model, either rule-based or model-based, that looks at individual characters to split, and then you give these sentences to your tokenizer, and it splits them into your tokens. So the normalizer, think of that as something that just sort of like cleans up things. So sometimes in some of these pipelines, you'll see tokenizer and then stemmer, or tokenizer and lematizer, and then a normalizer. Stemming and lemmatization are other ways of normalizing. It's just sort of, you don't want Tylenol with and without capitals, Tylenol with a comma at the end. You don't want these to be different tokens. You want to sort of collapse them into one thing. So the normalizer will take care of this for you. So we have a spell checker. So we all know the joke about doctors' handwriting. Well, it turns out their typing is not much better. So we need to correct spelling often. So then we have the sentiment detector. So here we have the Vivek N sentiment approach. So if you look at that paper, it's pretty interesting. They take the naive Bayes approach to sentiment detection, and they add some feature selection. They add, they add feature selection, n-grams, some other interesting stuff. It's a pretty good and easy to read paper. So what we have here is we have a set of positive and negative examples, and it's going to load that into the detector. And then we have the finisher. So imagine if we have something in Spark. So we've loaded into documents, and now we have a column with that struct type for the document. We've gone through, and now we've created columns for the different annotators. Well, I want to pop this out and send it to one of Spark ML's algorithms. Well, all of Spark ML's algorithms, what do they know? They know arrays of strings or just strings or stuff like that. So we need to break it out of the Spark NLP stuff and put it in a form that's going to be more familiar to Spark ML. So the finisher does that for you. It takes your annotations, you tell it which annotations to take out, you tell it how to take them out, and then it just gives you this data frame column for you to pass along to the vanilla Spark ML stuff. So here we have our pipeline. So the pipeline is, we take the text, we build a document. We split into sentences, we split those sentences into tokens, we normalize those tokens, we fix the spelling, we then do sentiment detection with our pre-built model, and then we have a finisher which pulls out the interesting stuff that we found. So I believe this is these are segments of one of the example notebooks. So you can go and download this notebook and actually run it and see how it looks. But I'd also like to remind you that later on today, at 2 p.m., we are giving a deep dive, a two-part deep dive. We're actually going to be looking in more detail at some of these notebooks and covering some of these topics. Any questions? Yeah, so let's go back to the tokenizer. Here we go. So here it's just showing the simple arguments of tokenizer, but there are other arguments available. And I would say that for any NLP library worth its salt, you have to be able to customize stuff like that because not only is it going to be, as Dave was talking about, like it's like medium dependent, it's problem dependent, but also sometimes it can be dependent on how you're storing the data. Like different hospitals may store data in different ways, and so there will be lots of different things you need to customize your particular problem. So yeah, a lot of these annotators, they come with tons of options, and they're all pretty well documented on the website I showed earlier. Yes? So I would say this would be something you do as a pre-processing step to querying. So you would go, you would find, maybe you have like a custom dictionary, you want to annotate these words, and then you want your search algorithm to increase the score for those special words. So you can use this library to create custom documents and then index those.
How long does it take to run for a single document? Is it real time or sort of suppose a single like a page, an article, or email?
So I would say Spark's use case isn't really single document stuff, but we do have a light pipeline that was released recently that's more for these smaller use cases. So as far as how long it takes to do a particular document, kind of depends on what you're doing and the document itself. Is it a clinical note or is it Moby Dick?
No, I mean something short, email to parse and annotate and do all the steps that you described.
Yes, so I'd say in general, the light pipelines were built exactly for that purpose, and we've had applications where basically we have a server-based solution and we get an API call and we need to process the document within tens or hundreds of milliseconds. So we definitely have those use cases running now. Yes?
You guys gave speed as a metric, but accuracy is fairly important.
Yes. Yes. That's a good observation, yes. If you don't care about accuracy, you can get really fast. General trade-off.
So how would it compare to like Spacey?
Yeah, exactly. Yeah, so for these specific use cases, yes, we did measure accuracy, and it was for comparable or slightly better accuracy. I just didn't put in the slides here. If you read the blog post, in the blog post we compare accuracy, speed, and scale. Yes. Good point.
I have a question. On your page said what makes language hard. You said medium specific. The example is see you in 15 minutes. Do you have any like algorithms or functions which can improve to solve this problem and improve the accuracy? Thank you.
Sure. Yeah, the short answer is yes. That's part of what we'll talk about. One of the topics for the afternoon, for the deep dive, is how you train your own domain-specific models. So we'll show some example of things we did, and then you could see some of the things that are pre-built in the library. So if you have annotated data, you can train your own. Okay, I think we're at time.
Yeah.
Yes, so thank you, everyone, and we'll be here for more questions if there are. Thank you.